Hey guys, I didn't quite finish what I wanted to show you in our Zoom on Tuesday because I guess I just talked too much. So I just wanted to start from here real quick. So we talked about getting heads and a tail on this experimental probability was 2 out of 8, or no, it wasn't, it's 3 out of 8. So 1, 2, 3 times that happened. So it says, so different scenario. Suppose you toss a coin 100 times and you get heads 20 times. What's the experimental probability that you get heads? Now we're not talking about theoretical now. We're talking about after doing this experiment 50 times, the experimental probability happened 20 times. So the experimental probability of getting heads is 2 out of 5. Well, we know in theory, 50% of the time you'll get heads. So the theoretical probability would be 25 out of 50, right? So the experimental and theoretical probabilities don't always match. However, you'll find it's been proven that the more experiments you do, the closer those two numbers will get to each other. So based on this experiment right here, suppose you toss a coin 60 times and you get tails 25. Oh, I'm sorry, different scenario. Suppose you toss a coin 60 times and you get tails 25 times. What is the probability, what is the experimental probability of getting tails? So that's going to be 25 out of 60. And both of those numbers can be divided by 5. So 25 divided by 5 is 5. 60 divided by 5 is 12. So you could say the experimental probability is 5 out of 12. Or if I turn that into a decimal, 5 out of 12 is about 0.42 or about 42% of the time that happened in this experiment. Suppose you plan to toss the same coin 10 more times. About how many times would you expect to get tails? So based on the experimental probability of 5/12, so we're going to do 5/12, and then we're going to set that equal to what happens if we do that 10 more times. Well, 10 more than 12 would be 22. Right? And we want to know out of 22 times, how many times would I get tails based on my experiment? So here is where we can cross multiply or divide. So 12 times x is 12x. 22 times 5 is 110. And then when we divide by 12, 110 divided by 12 is 9.1, or we could say about 9 times total. 9 times total. So since we've already got heads 5 times or tails 5 times, we would say maybe 4 more times. The other way we could have done this is to take 10 and multiply it by our 42% or our 0.42, and we get 4.2, which is about 4 more times than 5. So 9 total. So 4 more times after 5, right? You understand? I hope I didn't confuse you. Anyway, so a couple of different ways we could estimate that answer. All right, you can write probability as a fraction, decimal, or percent. We already know that. An employee of the Great Toys Manufacturing Company checked 400 toy cars. Out of those 400 cars, he found that 12 are defective. Something was wrong with them. What's the experimental probability a toy car is defective? Well, as a fraction, we're going to write 12 out of 400. Of course, those two numbers are divisible by 4. 12 divided by 4 is 3. 400 divided by 4 is 100. So the fraction is 3 out of 100, which is equal to 0.03, not 0.3, that's 30 out of 100. Or we could say that 3% of the cars are defective. 3% of the cars will be defective. So based on that information, how many defective cars would you predict in 1250 toy cars that have been produced? Well, since we know our percent or we know our decimal, we can simply multiply the total times 0.03. So 1250 times 0.03, we could estimate that about, it says 37.5, or we could say about 38 toys are defective out of 1250. The other way I could have done that is, this is our grand total. This was my original fraction. I could cross multiply, divide by 100, and I would still get about 38. All right, Madison High School ordered 64 new soccer balls. The students found leaks in 5 of the soccer balls. Well, I write the experimental probability of finding a leaky soccer ball as a percent. So we're going to say 5 out of 64. I can turn that into a decimal by dividing 5 by 64. 5 divided by 64 is 0.870.078, which is about 8%. If I move my decimal 2 places to the right and round, I get about 8%. All right, the hospital kept track of the birth orders of babies of families with 3 children. The results are, all these things could happen if you have 3 children. Find the probability that the first 2 children are girls. So let's see how many total results there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 experiments, basically, when someone has a baby. I wouldn't call that an experiment, but you know what I mean. The first 2 children, here are 2 girls. So this is the birth order, girl, girl, and girl, girl. Those are the only 2. So 2 out of 10, or 1 out of 5, which is 20%, or 0.2. What about the probability of all 3 boys? So we already know 10 is our denominator. So how many times are all 3 boys? So right here is the only time that a family of 3 children were all boys. So 1 out of 10, or 10% of the time, or 0.1. About how many families would you predict have all boys and 200 families of 3 children? So basically, I would want to know what is 200, what is 10% of 200? So 2%, I'm sorry, 200 times 10% is 20. So out of 20 families of 3 children, 20 out of those families, based on this experimental probability, have all boys. James tossed a fair coin 8 times and got heads 7 times. What's the experimental probability that he will get heads after he has tossed a fair coin 80 times? Well, right now, 7 times out of 8, and we want to know 80 times. Well, we could cross multiply or divide, or I could go, oh, well, I know that 8 times 10 is 80, right? So 7 times 10 is what? 70. The experimental probability says that if he tosses the coin 80 times, he'll get heads 70 times, which is not the same thing as the theoretical probability, right? So it says James tossed a fair coin 8 times and got heads 7 times. Theoretically, this is a big hint right here. Theoretically, what will happen on his next toss? Well, theoretical probability doesn't have anything to do with experimental probability, you guys. So every single time you toss a coin, there's a 50% chance of getting heads and a 50% chance of getting tails. So theoretically, what will happen on the next toss? Theoretically, there will be a 50% chance, or probability, I should say, of getting heads. Do you understand? If I could write, you could probably read that. All right, when I do, let me erase this last section so we can read it. All right, so When the theoretical and experimental probabilities don't match, what might I do to make them match more closely? And the answer will be do more experiments, conduct more experiments. How do I make those numbers match more closely? Conduct more experiments. All right, last one. A spinner is divided into sections of equal size, some of which are red, some are blue, and the remaining are green. The probability of landing on a section that is red is 25%. The probability of the arrow landing on a section colored blue is 10%. What's the probability of the arrow landing on a section colored green? Well, the entire spinner is either green, red, or blue. The entire spinner is 100% of it, right? Well, we're going to add together the red probability plus the blue probability. And we know that 35% of the spinner is either red or blue. So to find out that the rest is green, we're going to subtract 35% from 100%. And the answer is 65% is the probability of the arrow landing on green. Do you understand? Because the whole spinner is 100%. So you have to subtract away the probabilities that they give you to figure out the probability that's left over from 100%. All right, guys, y'all did great in class on Tuesday. I hope you have a great day, and let me know if you need my help on anything. Bye, guys.